Hi and welcome to this video, which is covering hypothesis testing, which is part of the Inferential Statistics section of the Leaving Cert Higher Level course. So within this video we are going to look at 3 different ways which hypothesis testing can be done. But before doing it, I would strongly recommend that you have already revised Z-scores. To help, the video for Z-scores has been linked in the description below, along with the full complete Inferential Statistics course video. So doing hypothesis testing, we talk about the null hypothesis and the alternative hypothesis. Now, this part is so important. This will never change, and sometimes students really get bogged down in the idea of what the claim is, and the claim is the null hypothesis, and that is not true. The null hypothesis is always the idea of no effect or null effect or no change. So it will always be mu equals or p equals, and that will never change. It'll be mu equal or p equals. So the hypothesis test will be on one parameter or the other, and whichever one it is, that's what we'll use. The alternative hypothesis is then always the opposite to the null hypothesis, and that's to ensure we capture everything. So for example, if I said mu is equal to 100, the opposite of that is mu does not equal 100, and that covers everything. So it'll cover every single value. So it's either 100 or it's not 100. So we're kind of looking here about an exhaustive event. In this sense, we go back to probability, the idea that the probability of all of these would add to 1. So it's either going to be one or the other. So hypothesis testing of a mean value. So looking specifically at the mean as a parameter, there are 3 methods. So using the confidence interval, using z-scores, using p-values. And if we want to test for p, this is the only way to test p. And remember, p is the population proportion. So we only have one method. So 3 methods for testing the mean, but only 1 for p. Now, we'll work through these and we'll talk about when a specific method is favorable over another. What I would say is it's usually down to method 1 and method 2. We would never use method 3 to actually do a hypothesis test, because method 3 relies on already doing method 2 effectively. You need your z-scores. So you might question, well, why would you ever need p-value? And what has happened is, because nobody would ever choose to do them, they are added in at the end of a question, as in what is the p-value of this hypothesis test, and to comment on it. So it is really important, and because we don't have a choice when we get a question on it. So let's take a look at this example, which is a hypothesis testing question, and it's using the confidence interval for the mean. So a study of 50 Leaving Cert candidates, so that is N, so we're talking about a sample, in 2014, randomly selected in the Dublin region, found that they had a mean mark of 374, so that's X bar, and had a standard deviation of sigma. Find the 95% confidence interval mean mark in the subject in the Dublin region and interpret this interval. Okay, so the first thing we're going to do is we're going to write down our formula, which is X bar minus 1.96, and it's the standard error of the mean, which is sigma over root n. That is less than or equal to mu, is less than or equal to X bar plus 1.96 standard deviation over root n. So we start with 374 minus 1.96, 45 over square root of 50. It's less than or equal to mu, it's less than or equal to 374 plus 1.96, 45 over root 50. So working that through, we get 362 is less than or equal to mu, is less than or equal to 386. So that means we can state with 95% confidence that the mean mark of the population sits between 362 and 386 marks. Now, there was a follow-on question here, which was the hypothesis test. The mean mark in the subject for all Leaving Cert candidates in 2014 was 385 mu, and the standard deviation was 45. That's sigma, And John suggests, so here's my claim. I usually suggest that you use a different colour for the claim. The mean mark in the Dublin region is not the same as the whole country. So just to remind us, the mean mark in the whole country is 385. So it says test this hypothesis using a 5% level of significance. Clearly state your null hypothesis, alternative hypothesis, and your conclusion. So our first step is to state your null hypothesis, H0, and that is going to be mu equals, and our alternative hypothesis, H1, is going to be mu does not equal. And the question says 385, so that's what we're going to put in both places. So the mean mark in the Dublin region is the same as the whole country. So mean mark in the Dublin region is the same as the whole country. And this is then the opposite. So mean mark in the Dublin region is not, that's important, not the same as the whole country. Okay, now, so apologies for my writing, very hard to write on this screen. So the next thing I would suggest you do, and you're not going to get any marks for it, but it really does help to make your question a lot easier, is to identify which one is your claim. So often the assumption by students is your claim is your null hypothesis, and that is not always true. Sometimes it is, sometimes it's not. The null hypothesis must be mu equals. Remember that this is a mathematical process, so the maths can't change. The maths has to stay the same, so it must always be mu equal to. You can't sometimes do a sum and it'll give you mu equal, and sometimes do a sum and it gives me mu does not equal. That's not how it works. So the claim is something different to your null and your alternative hypothesis. So go back to what it says. John suggests that, highlighted in green, the mean mark in the Dublin region is not the same as the whole country. So I'm going to make a little note here that this is my claim. And that helps me as I finish off my question. If I decide to reject my null hypothesis, I'm effectively accepting my alternative hypothesis, which effectively accepts the claim. If I accept the null hypothesis, I'm rejecting my alternative hypothesis, and by then I'm rejecting that claim. So it just helps to structure the question a little bit. The next thing we're going to do is we're going to do some testing. Now, I did say that there was 3 ways to do these hypothesis testing questions. However, we are looking specifically at confidence intervals. Remember, part A of this question, we actually worked out the confidence interval already. So we had 362 is less than or equal to mu is less than or equal to 386. So that would be our testing portion. If we hadn't done it in part A, you would have had to do it there or an alternative method. After that, we do what's called the results. Now, the results, it's a mathematical result. So let's take a look at this. The null hypothesis says mu is equal to 385. The testing, so the confidence interval we did, the 95% confidence interval for the population mean was given as 362, between 362 and 386. So based on that, does it look correct? And yeah, because if you look, 385 does sit in that confidence interval. So what we would say, since mu equals 385 sits in the above confidence interval, and the language we use here is we fail to reject. The null hypothesis. Okay, so that's the result. But they specifically asked us for the null hypothesis, alternative hypothesis, and a conclusion. Now the conclusion is different to your result. So the conclusion, that's going to link back to the question. What we would say is we can conclude with 95% confidence, or a 5% level of significance. That the claim that the mean mark in the Dublin region is not the same as the whole country is, and I'll do this in red as well, incorrect. Okay, so make sure you have all of your steps. Make sure that you're including a conclusion. So your results, remember, mathematical base, your conclusion is going back to the question. This is a very structured question and the steps remain the same no matter what. We'll always state our null hypothesis, alternative hypothesis. We'll always do a section on testing. That bit can change. The results and conclusion will always sound somewhat very similar. So let's look at a question that asks us to do a hypothesis test, but this time for the parameter proportion. In an upcoming election, two candidates are campaigning based on the unemployment issues in one of the countries. One of the candidates believes, so as soon as we see a word like claims or believes, we know that this is our claim, that 59% of the voters support him. He arranges for a random sample of 504, so that's N, supporters to be selected. Of this sample, 360 people said that they support the candidate. Okay, so that 360 there doesn't actually belong to a specific letter, and we don't have anything to call this as such. We are going to have to work with p hat. But p hat is the proportion of people in the sample. Now, this is definitely not the proportion of people in the sample. This is the actual number. So to turn this to a proportion, we put 360 all over 504. To help us out a little bit with that, we'll turn it to a decimal. So that's 7143 to 4 decimal places. Okay, so that's something I would do as we work through it. But you can also wait till we get to that part within the answer of the question. Test the hypothesis using a 5% level of significance. Clearly state your null hypothesis, your alternative hypothesis, and your conclusion. So to make it a little bit easier to read, I have actually this typed as opposed to me writing it, which will also speed up the question. So the null hypothesis is going to be based on my proportion, which I actually forgot to underline and mention here, and that is P. So it said that within the claim. So my null hypothesis is P equals 59%. My alternative hypothesis is P does not equal 59%. Now, confidence interval for the proportion we've already done, but when we come to hypothesis testing, although it is very similar to hypothesis testing for the mean, there is one very significant difference that it will be good for you to note, and that is writing the null hypothesis and the alternative hypothesis in words. And I'll explain why. So looking at this, the null hypothesis in words would be that 59% of the voters support him, and that will be absolutely correct. However, if you do write it like that, what is the opposite? So often students say 41%, but if you're saying 59% or 41%, what about all the other percentages? Remember, this is supposed to be an exhaustive event. Our alternative hypothesis is P does not equal 59%. So would you say 59% of the voters don't support him? But that's also not right, because 59% of the supporters voting, that 59% of the voters support him and 59% of the voters do not support him. They're not exhaustive events either. So it's really important that you reword these, so it'll always happen in proportion questions. This isn't just this particular question. It will be always in proportion questions. And the way I would suggest you write it is this. The proportion of voters who support him is 59. So I'll always start my sentence with the proportion of, then whatever the question is about is 59. And now if I said to you what's the opposite of that sentence, hopefully it'll be a lot clearer, and that is the proportion of voters who support him is not 59. And now we have it all covered. We now have the full exhaustive event covered. So once we have the null hypothesis and the alternative hypothesis stated, we get into the testing. Because we're dealing with proportion, we're going to look at the 95% confidence interval for the population proportion. And here's our formula. So we're going to sub in the letters we have are n equals 504 and p equals 0.7413. So you would show your substitution and work through it. I am running a little bit short for space, so I'm going to go straight to 6749 is less than or equal to p is less than or equal to 0.7537, and because we're working with percentages in my hypothesis, I'm also going to turn this to percentage. 67.49% is less than or equal to p is less than or equal to 75.37%. Now, if you want to work through that in more detail, the previous examples of working with the confidence interval for the population proportion are available in this video if you're watching the complete inferential statistics video, or it will be a separate video under confidence interval of the population proportion. So that is the proportion. So that's my testing piece, so I get to my results. So look at that p, what we want for the null hypothesis, p equals 59%. It's not looking good. That 59% is not in that interval. So what we would say is, since p equals 59% does not sit in the above confidence interval, we reject the null hypothesis. And the last step then is to bring it back to our conclusion. So based on the above, we can conclude with a 5% level of significance that the candidate's claim that that 59% of the voters support him is incorrect. So one of the things I didn't do that I would suggest that you would do as you're working through it, you would mark this as your claim. So usually it's more important if the claim is not the null hypothesis. So if it is, generally I will forget, but generally students will just work through it. But it's just, if it's not the null hypothesis, it's really important to note that for yourself. So let's talk about z-scores. So using z-scores to test your hypothesis is a very useful method, especially when you've not already created a confidence interval. So in the previous example, we saw that we created a confidence interval and then used it. So if we didn't already have the confidence interval created, is there an easier method? In my opinion, z-scores are an easier method. So since we work only with 95% confidence or 5% level of significance, we always compare our z-scores to 1.96, and that is a plus and a minus 1.96. So that's going back to what we would have learned at the very start of our inferential statistics. And in order to calculate a z-score, we have a formula that's very similar to our standardizing formula that we would have seen before. And this formula is on the top of page 35, and it's called the one sample z-test. And it's just underneath the heading that says hypothesis test. So that is z is equal to x bar minus mu all over sigma all over the square root of n. So some things that give us a hint that it's about a sample. Well, in its name it has sample. X bar implies the sample mean, and n implies the number in the sample, so the sample size. So let's take a look at using that. Acme Confectionery has launched a new bar called Chocolate Crunch. The weight of these new bars are normally distributed with mean 4.64 grams and standard deviation 0.12 grams. So as I'm working through this, I'm underlying anything important. So my mean is given as mu and my standard deviation is 0.12 grams. A sample of 10 bars. Okay, that's my n. I select it at random and find the probability that the mean weight is between this and this. Okay, so the first thing I'm going to do is I'm going to write down the probability that the mean weight is between, so that's x bar, sits somewhere between these two. Now, this is linking to our central limit theorem. Can I state that the sample is normal? And just to highlight how many things are in my sample, we have 10 bars. So just as a reminder, we had, once the sample was big enough, any sample, regardless of its underlying distribution, would be normal. And that is if we had 30 or more in the sample. So if the sample size was 30 or more, our sample size is only 10. So will I be able to use the normal distribution? And the answer is yes, I can, because this is a special case, because the underlying population we were already told is normally distributed. So the sample will be normally distributed regardless of sample size. And that's important. The central limit theorem is more important for us when we're dealing with populations where the distribution is not normal or not known. Then once the sample is 30 or more, we can assume, okay, the sample will be normally distributed. However, because we know in this question that the population is normally distributed, we can say for sure that even with a sample of 10 bars, it will also be normally distributed. So we can go straight to our z-score formula. And the z-score formula is z is equal to x bar minus mu all over standard deviation all over root n. X bar, we have 2. We have to do x bar equals 4.6. That'll be 1. And we'll do x bar equals 4.7. That's the other one. We have mu, which is equal to 4.64. We have standard deviation, sigma 0.12, and we have n is equal to 10. So that will remain constant. So z is equal to 4.6 minus 4.64 all over standard deviation 0.12 all over square root of n. This one here is going to be z is equal to 4.7 minus 4.64 all over 0.12 square root of 10, and we're going to get our two z-scores here. So when we plug those into the calculator, we should get this as minus 1.05. It goes 4 zeros, so we round to 2 decimal places, and this gives me 1.58. So really what we're trying to find, the probability that we have minus 1.05 is less than or equal to z is less than or equal to 1.58. Now, I'm very much a fan of drawing this out, get a sense of what's going on, your normal distribution. So just a rough sketch. So here's my normal distribution. We have here in the center, so here is about minus 1.05, and about here is 1.58, and we're trying to find this piece in the middle. So what we're going to do is we're going to get the probability that z is less than or equal to 1.58, but then we're going to take away this piece at the end, because I'm going all the way back to the left, so the probability that z is less than or equal to minus 1.05. Now, that won't work, so instead what we have to do, so this one's fine, sorry, it should be 5.8. This one's fine, and instead what we have to do is it's going to be 1 minus the probability that z is less than or equal to 1.05. So how we got that, I'll do a second sketch. So there's my minus 1.05. I'm trying to take that part away. I can't, so instead I move up to the other end, which is 1.05. I can't even work that out, but it's 1 minus the probability that z is less than or equal to 1.05. And that's where I got my answer down here. So we are able to look up the tables and work this out. So we're looking at page 36, 37. I'm just going to draw a line down here so we can keep track of what we're doing. And we should get 0.9429 minus 1 minus 0.8531. You can put that straight into your calculator with the brackets as is. Make sure the brackets are like this, and we get 0.796, which is 79.6%. So that's how we would work with a sample, but knowing that the underlying population is normally distributed, we don't need to apply the central limit theorem. So the mean lifetime of light bulbs produced by a company has in the past been 1,500 hours, so 1,500, so that is mu. A sample of 100 bulbs, so that's n, recently produced by the company have a mean lifetime of 1475, so that's X bar, with standard deviation 110. Test the hypothesis that, okay, the mean lifetime of the bulbs has not changed. So they're saying it has not changed, therefore it is still 1,500 hours. So that is their claim. So the first thing we're going to do, we're going to state our null hypothesis and our alternative hypothesis. So what we're saying then for the null hypothesis is mu is still 1,500, so the mean lifetime of the bulbs has not changed. And then the alternative to that will be the mean lifetime of the bulbs has changed. So sometimes students get bogged down in the word not appears here or somewhere else. Like we've seen now examples where the not has appeared as the null hypothesis and as the alternative hypothesis. So just be so careful. It is much better to try and understand the question and make the connection between what is being asked and what the null hypothesis means. So remember, we're always dealing with mu equals, and that would mean mu equals 1,500, and if it was still 1,500, nothing has changed. So our claim is actually equal to our null hypothesis. So this is our claim. So after we've stated our null hypothesis and our alternative hypothesis, our next step is testing. Now, that's what's going to change in this question. This time for testing, because we haven't already done a confidence interval, we could create a confidence interval, but there is a slightly easier way, and that is using the z-scores. So we're going to look at z-scores, and remembering that for a 5% level of significance, we're talking about minus 1.96 is less than or equal to z is less than or equal to 1.96. So our formula here from the top of page 35 is z is equal to x bar minus mu sigma over root n. So let's get some letters. So x bar was 1475. Mu from the question was 1,500. Standard deviation sigma is 110, and the sample size was 100. Therefore, z equals 1475 minus 1,500 all over 110 over the square root of 100, and working that out we get minus 2.27. So looking at that z-score, we're going to compare that z-score to what we expect our z-scores to be. So we expect our z-scores, like I have written here, to be between minus 1.96 and 1.96. So that's what we expect. So since z equals minus 2.27 does not sit in the above interval, we reject the null hypothesis, and the above interval is this one here. So above interval, we are talking this one here. So for z-scores, just in case you were wondering, oh, what interval, because we don't have a confidence interval, that is true. But this time we're talking about the z-score interval. So between the z-scores of minus 1.96 and 1.96. So we reject the null hypothesis, which means effectively we're rejecting the claim. So based on the above, we can conclude with a 5% level of significance that the mean lifetime of the bulbs has changed. So the z-scores, as you can see here, they're just a little bit neater. They work a little bit quicker. We're not messing around with a really big formula to remember. This formula is given in the log tables. With the interval, you're kind of doing two separate sums. I personally prefer this method. There will be nothing to stop you using the confidence interval in this question, because there is no reason for them to say do one way or the other. However, if you're already asked to do a confidence interval, you might as well use it. That's our thinking here. But this question, there was no lead up to it. You could have used either method. This is us looking at how z-scores would work. So the final thing we're going to look at with regards to inferential statistics, it's the p-values. So p-value itself stands for probability value. So this is the probability of getting results at least as unusual as the observed mean, given that the null hypothesis is true. Okay, now that is great, but can you understand what that means? So we're going to really break down the p-value so that you understand it and you can make a much better attempt at approaching these questions. Because often what I find with p-values, students really struggle and tend to learn things off. And once you start learning things off, it doesn't make any sense. You just get absolute rubbish in these questions. But basically, in simple terms, the p-value will give us a percentage which we can compare to our standard normal distribution. So let's take a look at our standard normal here. We have a set of possible results. We have very unlikely observations here on the left and on the right, and the true value of the null hypothesis and most likely observations are there in the middle. So there's a 95% statistical significance threshold. And this is important because this one here, that's basically 1.96. And there's a matching one that is just about here, I think, and it's minus 1.96. And everything within that is good. So I'm going to do this in kind of a green color. So this is good. Everything in there is what we want. And these outside pieces, these tails, these are what we call the rejection region. And this rejection region is what we're going to focus on when we talk about our p-values. Now, we've already talked with regards this shape and 95%. So let me go back to this idea. I have change color, 95% of my data here, which means there's 5% in the tails, which means down here is 2.5% and here is 2.5%. But we're going to work with our tails together. So with our p-values, we want to compare our answer to the standard normal distribution, which is here on our left. Since we're dealing with 95% confidence or 5% level of significance, we want to ensure that our answer sits inside the middle 95% of our data. So basically those z-scores, those minus 1.96 and 1.96, we wanted to sit between those, and that's where we're 95% confident. If they sit outside those, that's getting into our 5% level of significance. That's where we're kind of worried we're wrong, because it's in those tails. It's in those areas where we're not sure. We really don't think that's going to work. They're what we call, remember, our rejection regions. So if the p-value is less than 0.05 or 5%, it means that it's sitting out in our tail. So if it's less than 5%, we're going to think of it as being out in that rejection region. If it's greater than 0.05, that means that it will sit in the main 95% of our graph, and we fail to reject it. Okay, so if the p-value is bigger than 5%, it's beyond our tails, because remember we only have 5% between our tails. So if it's bigger than 5%, it's going into the middle, and that is good. So we're going to talk about calculating the p-values, and just to say before we start into this, so this is a very mathematical way that we're going to go through it. This is really kind of what you would see in the workings. However, I find that students often struggle with this to understand it. So as we're going to go through the example, what I'll do is I'll use a very visual picture like we would do with all of our z-scores to really try and understand what's happening. I would definitely be using a more picture-based or a diagram method as you're working through the examples, just for yourself to use so you can really get a sense of it. I think learning off these kind of formulas not going to be hugely beneficial unless you really understand what's going on. So to calculate p-values, we must first have the z-scores. And I did say earlier that actually we would never use the p-values for hypothesis testing, because if I worked and got the if I wanted to do p-values, I'd first work and get the z-score. So if I got the z-score, would I not just go straight and compare the z-score to minus 1.96 and 1.96? So this is why they asked this question specifically as an extra question, a follow-on piece after you've done hypothesis testing. So in order to calculate our z-score, we must first use the one sample z-test on the top of page 35. So we've seen this a few times now. And then we work from our tables and we work out 2 times 1 minus the probability the z is less than or equal to the z that we've just worked out. So from page 36 and 37, our log tables, we know that we have the standard normal tables. We're going to use 1 minus the probability to get the right of our z-score, so to get the tail, and we're going to multiply it by 2 because we want to double it. So remember, our rejection regions, plural, they are each of the tails. There's 2.5% in each tail, so to get our 5% we would have to double one of the tails. Now if that seems like I haven't a clue what's going on, that's absolutely fine. Wait till you see the example and hopefully it will make more sense. So I'm going to do an example that is following on from a hypothesis test. So again, if you're watching the Inferential Statistics the complete course straight through, you will have already seen part A. If you're watching just the p-values, you can go back into the hypothesis testing, and we did this in the Z-score video, that part A. So I'm going to work through the part A because it has some very valuable information. That's why it's here. So the mean lifetime of bulbs has in the past been 1500, that is mu, and a sample of 100, that's n, as recently produced by the company, has a mean lifetime of 1475, that's x bar, and 110 is my standard deviation. So test the hypothesis. And actually this was not true. Spoiler alert. Not true. So we rejected H0. Now the reason I'm telling you this is because that will actually impact on the next part, because the p-value, what we decide with p-value, should also match what we did in our hypothesis test. So if the p-value tells us to reject, we should have rejected above. If it tells us to fail to reject or accept, we should have also done the same above. So it should always match. You're not going to get conflicting answers. So find the p-value of the test you performed in A above and explain what this value represents in the context of the question. So the first thing I'm going to do is I'm going to figure out what is my z-score. So z is equal to x bar minus mu all over sigma over root n. So x bar is given as 1475. Mu is given as 1500, sigma is given as 110, and n is given as 100. So going through my z-score here, 1475 minus 1500 all over 110 square root of 100. Working that out, we get minus 2.27. So what we're trying to do is we're trying to figure out, well, how much lies outside of these tails. So 1, 2, so 2.27. So I'm going to say that that's here. And this is my tail for minus 2.27. But I also want to include the other tail because what I want is a two-tail test, and I want both end or both tails to be included, because remember our 95% sits in the middle. So here's what I have, and I'm trying to figure out, well, how much or what percentage of the data lies in each of the tail. So I'm not going to bother with the negative because I can't work with the negative. So instead I'll work with the positive here. Now if I asked you, can I work with this piece here? Hopefully your answer is no. If you go to the top of page 36, you'll see that we can only work with the z-score when we're working to the left. But we do know that the total area under the curve is 1. So this part here actually gives me 1 minus the probability that z is less than or equal to 2.27. Now, when I work that, and I'm going to do a little bit of that here, so 1 minus the probability that z is less than or equal to 2.27. What I will do with my answer is I'm going to double it, because remember I have two tails. So I'll get my answer for up here, but I also want my answer, so let me get the highlight so you can see it clear. So I'll get my answer for up here, but I also want my answer for down here. So going to my tables and looking up 2.27, what I get is 2 times 1 minus 0.9884, which cleaning up gives me 0.0116, which gives me 0.0232, which is 2.32%. So there is 2.32% of the data on those edges. Now, go back to 95% confidence, 5% level of significance. We can only accept this if it's bigger than 5%. Once it's smaller than 5%, it's too far out in the tails. Think about where our 1.96 is. So there is our minus 1.96. There's our plus 1.96. Everything this side and here, they are my rejection regions. So that's my rejection region. And there's my rejection region. So it's too far out. It's not in that center 95%. So this is my 95% where I'm so happy, I know everything is good. But those two little tails sit outside in my rejection region. So since 2.32% is less than 5%, we reject the null hypothesis. H0. And that's thinking back to the previous part. And go back, we already have said that the rejection we've already said that we rejected the null hypothesis in part A. So that one matches. So that's really important. I suppose just the last part of this is explain what this value means in the context of the question. So a nice quick way to answer that would be to say that the probability of accepting the null hypothesis is 2.32%. Since that's less than the 5% chance that we're wrong, so keeping that as really casual terms, but I suppose just for you to understand it, because that 2.32% is much smaller than the 5% chance I'm wrong, that's not good. So if that was bigger than 5%, that would be okay. So explain what this value represents in the context of the question. So the chance of accepting the null hypothesis is 2.32%. And that is sufficient. All the work you've done, everything you've shown, and that will get you your answer.